Hello, in this class we will be describing on the drying principle and different kinds of dryer, their mechanism, and the drying curve in typically bio products, how it happens. We will be discussing on those aspects. So basically, drying process falls into particularly three categories. We will be saying primarily air and contact drying under atmospheric pressure, where air is coming in close contact, heat is being transferred between aqueous phase and air, which is going to take out the moisture along with the air. So heat transfer and mass transfer is taking place. The other kind of drying can be vacuum drying. Actually, in this case, heat is not directly being transferred, but vacuum is created. So low pressure actually causes removal of moisture, or water can be easily evaporated at a lower temperature. So and some amount of heat when is required, it can be provided by radiation or conduction heat required for the drying process. And the last one is freeze drying, which is actually more important for thermolabile material. So it is sublimed from frozen food or maybe some products which is maintained at very low temperature in ice conditions, and here product stability is much higher compared to the previous two process. We will be discussing these three kinds of drying process in little bit more detail in coming slides. Now if we discuss about the heat transfer process and how is it going to dry, we need to understand the drying process itself. So essentially, heat transfer in this drying, we are discussing a heat energy requirement for the drying process. The rate of drying actually can be determined by how much of heat is transferred and how much mass, means water removal. So in some circumstances, the rate of mass transfer can be the limiting one. In some cases, the heat transfer may be exposure to heat may not be sufficient, and maybe all the mechanism in heat transfer, conduction, radiation and convection may take place in terms of drying. And we all know, if I am going to talk about the heat transfer process, it is often referred as Q. HS, Q equal to the amount of heat transferred, HS into A TA minus TS. So A is the surface area. Increased surface area will provide more amount of water molecule to be evaporated from the drying surface. A is the surface area, H is, we can say, specific amount of heat required per unit mass. So this is some constant which can be related with the material involved there. Now we'll be discussing one slides on drying curve, how it happens when we are having sufficient amount of moisture, how the drying process takes place. So if I see some biological material, maybe some moist powder or maybe some bio-based products, so initially we will have some time which is for equilibration time, very short period of time in the drying cycle. Then we will see here a constant drying period and a falling drying. So we will be discussing all those aspects over here. So first portion is settling down. So the drying air is coming in contact with your material, so they reach one equilibriums with the drying air, the surface. The constant rate drying means from the particle, inside the particle, water is coming out to the surface, and from the surface water is getting evaporated. So if the rate of water transfer from core to surface is higher, then there will be no shortage of water. Moisture will be always there on the surface, and drying rate can be constant. So rate of mass transfer is going to balance the heat transfer process. So it is a constant rate of drying, same amount of water moisture is getting removed, there is no shortage. So here you can see moisture content versus drying time, it is really a constant one. And the falling rate period means once the core water, most of the core water releasing into the surface has been removed, then the surface starts drying up, and the heat cannot really remove the amount of water what it's supposed to remove, because water is still core inside the core of your material, which cannot come out, and as it is not coming out, drying rate falls. So the surface begin to dry and the drying rate changes or maybe getting lower, that is known as falling rate period. Anyway, some of the people actually distinguish the falling rate period also into two different, fast falling and slow falling rate period, but essentially this is not a required one. And if you say how much of drying is taking place for any material, we can see the amount of water removal with time, that is actually drying rate. You can see we are writing a little bit expression here, pi by 6 dq rho s. Actually, that talks about the volumetric size of a particles. Omega, so this is volume, this is density, so mass of the particle, and omega is the moisture content. So pi by 6 dq rho s into omega is the total amount of water which is going to be removed, so water amount essentially. So d water amount dt, it is actually going to be proportional with the surface area, and surface area can be related with d square, so pi d square, and ji is the flux. So we can say, for example, here if we say the same corresponding unit in this case can be related with the mass removal rate, and here it is surface area. So mass per unit surface area, how much of water molecule per unit time is getting removed, so that is known as flux. So essentially we can write like this way. And the heat transfer amount can also be written as the amount of heat transferred is T minus Ti, proportional to T minus Ti, that is temperature in the bulk air and maybe a temperature in your drying surface, so difference is there, and that is IJI, and we can actually compare these two and correlate. So essentially it is becoming, instead of this flux, we can write H into T minus Ti by lambda. So lambda is actually a proportionality constant, we can say, which is going to relate with the amount of heat transfer. So if I plug it here and make the derivative, we will have d omega dt, that is the moisture content, change in moisture content, and we can simplify and we can find out that this is going to be proportional with T minus Ti. So d omega dt is a function of temperature gap between these two. Now the different kinds of dryer we will be discussing. Primarily we are discussing here, for example, vacuum tray dryer. Vacuum tray dryer, we can show over here one from thermoscientific, one figure has been provided just for understanding. Vacuum tray dryer works by removing the moisture through a vacuum it creates. So essentially vacuum is created at the end of a tray where you are keeping your sample, and the vacuum, at the end of the vacuum there is a condenser which will condensate the water molecules, so drying process continues. So it can of course the container will be actually closed one which can withstand the vacuum pressure, so that is essentially required, and so drying will be more easier here. So oven is also connected with the vacuum pump, so tight environment is given, so the drying will take place, and we are keeping the sample over the tray for drying. So water vapor is going to be condensed and removed from the tray. A simplistic design anyway, and it is useful for those material which are sensitive for heating. So thermolabile material may be preferentially used for vacuum tray dryer. Spray dryer is even more advanced. And here actually the cost may be higher, but the regular processing cost may be lower. So maybe purchase cost is high, but operating cost is lower compared to the earlier one. So spray drying actually transformation of fluid, that means a slurry or maybe a solution. It is being atomized, so very small fine droplets is created, so increasing the surface area, and hot air is circulated through the chamber, so the droplets get solidified. The water is getting removed quickly on flotation. So this process is primarily three steps. One is atomization, droplet to particle conversion, and particle collection. Droplet to particle conversion means removal of moisture from the fluid, which is causing it to solidify. So starting material has to be liquid paste so that it can be atomized through the nozzle, which is the first step here, atomizer. The small droplets are sprayed, and hot air or hot gas is provided here. So this is dried around 150 to 250 degrees centigrade. So very quickly, hot stream of hot air or maybe gas we are utilizing for drying process. And then we need a separator also. Cyclone separator is used to collect those particles for collection purpose, and the exhaust gas can finally remove. So small droplets have relative high surface, so they are drying very easily. And finally, after the drying process is over, we need to collect it. But two things here you need to know: the small droplet is always preferable, so you'll have high surface area, very fast drying, and it will be completely dried within seconds. And evaporation actually prevent from overheating, because as it is evaporating from the surface, so it will cause a cooling effect. Latent heats is being utilized, so your material will remain comparatively at low temperature even in the hot air or gas environment. The next portion is for freeze drying, or which is very essentially we use for biological molecules. So here we are showing the phase diagram for water, particularly liquid, gas phase, and solid phase. So ice, liquid, and vapor. So we always see there is a triple point temperature on which all the phases are existing over here. So from triple point we can move actually. If we increase the temperature, the compound will become in vapor phase. If we reduce the temperature, it is becoming solid, and similarly increasing pressure will increase its solidification, and decreasing pressure will make it in vapor phase. So essentially freeze drying, we are having our substance in liquid phase. So rather than providing temperature which is on the x-axis side, we can do the opposite one. We will actually reduce the temperature, so making it a solid, and then the pressure is reduced. So from solid phase it is coming down this axis, y-axis, and so water is removed, water phase is removed directly without heating. So this is called sublimation process. So here one freeze drying equipment shown, mostly used in laboratory scale anyway. So it has some stages, particularly we'll say 4 stages. One is pre-treatment, that is we are converting or we are changing the solvent where we are going to use for our compound, maybe increasing the concentration of your slurry. So these are before you are utilizing the freeze drying. You may need some of the steps. You may need to increase the surface area so that drying process will be increased. So, or maybe reformulation, changing the solvent, those kind of things can be done. That is known as pre-treatment. Then we have to freeze it, that means lowering the temperature, we make it solidify, so water will form ice. So freeze drying in this step is very much important, and we are keeping this temperature below triple point, so somewhere in this zone, below triple point means this zone here solidified. So once at this point, if a sublimation is taking place, then from solid to vapor phase transition will take place. Now primary drying is actually reducing the pressure. So in this case the pressure is reduced to few millibars. So and we will be providing some small amount of heat just for sublimation process it is required. So ice will be sublimed to vapor phase, and of course these all things are done at very low temperature. This drying process takes place very fast also in some cases depending on the surface area and pressure you are utilizing. So once most of the water has gone, so some residual water may be still there, so some 4 to 5% water will be there. So in that case what we'll be doing, we'll be we'll be decreasing the pressure further, and we may need to provide the heat in terms of radiation heat kind of thing. So those water molecule can be removed, so unfrozen water molecules then be removed in this process. So it will be heated to a temperature where physical and chemical interaction between water molecule and your target compound can be broken. So essentially these four steps will result in a freeze dried products, which is most often used in biological process.